To obtain the optimum performance from paints, it is important that the metal surfaces are properly prepared before application of paints and subsequently maintained as such throughout the fabrication and erection process. Paints tailored for the service conditions of the structure to which they apply, and recommended as such by the manufacturer, only should be applied. It is common, especially for ships undergoing a regular dry docking, for the coating process to be specified and managed by the coating supplier. Good surface preparation is essential to successful painting, the primary cause of many paint failures being the inadequacy of the initial material preparation. It is particularly important before painting new steel that any mill scale should be removed. Mill scale is a thin layer of iron oxides that forms on the steel surface during hot rolling of the plates and sections. Not only does the non-uniform mill scale set up corrosion cells, as illustrated previously, but it may also come away from the surface, removing any paint film applied over it. Any corrosion from storage of the steel outdoors in a stockyard must also be removed. It is also important to create a good surface for coating. Swedish standards are often quoted, SA3 being white metal and SA 2.5 being near white metal. SA 2.5 is common as a reasonably achievable standard for shipyards. The surface is clean and the blasting process also provides a key with very small indentations to which the coating adheres well. The most common methods employed to prepare steel surfaces for painting are blast cleaning, pickling, flame cleaning, preparation by hand and high-pressure water blasting. Blast cleaning is the most efficient method for preparing the surface and is in common use in all large shipyards. Smaller shipyards, where the quantity of steel processed does not justify the capital investment in the preparation equipment, usually buy steel already prepared from a steel mill or stockist. Following the blast cleaning, it is desirable to brush the surface and apply a coat of priming paint as soon as possible, since the metal is liable to rust rapidly. There are two main types of blasting equipment available: an impeller wheel plant where the abrasive is thrown at high velocity against the metal surface, and a nozzle type where a jet of abrasive impinges on the metal surface. The latter type should preferably be fitted with vacuum recovery equipment, rather than allow the spent abrasive and dust to be discharged to atmosphere, as is often the case in ship repair work. Impeller wheel plants that are self-contained and collect the dust and recirculate the clean abrasive are generally fitted within the shipbuilding shops. Steel shot is the preferred blast medium for preparation of steel plates and profiles for new construction. As the process proceeds, the shot is recovered and reused. The shot breaks down during the blasting, and a mix of new and broken shot provides good surface preparation. Dust and other debris is filtered out of the recovery system for disposal. Cast iron and steel grit may be used for the abrasive, also copper slag, but non-metallic abrasives are also available. Grit has been used in ship repair but is becoming much less popular because of environmental issues associated with disposal of the waste material. The use of sand is prohibited in most countries because the fine dust produced may cause silicosis. Pickling involves the immersion of the metal in an acid solution, usually hydrochloric or sulfuric acid, in order to remove the mill scale and rust from the surface. After immersion in these acids, the metal will require a thorough hot water rinse. It is preferable that the treatment is followed by application of a priming coat. Pickling is no longer found in most of the ship construction industry. Using an oxyacetylene flame, the mill scale and rust may be removed from a steel surface. The process does not entirely remove the mill scale and rust, but it can be quite useful for cleaning plates under inclement weather conditions, the flame drying out the plate. Flame, or another heating process, is used as part of an automated preparation line in a shipyard to preheat the steel, which assists the cleaning and drying of the primer paint coating. Hand cleaning by various forms of wire brush is often not very satisfactory, and would only be used where the mill scale has been loosened by weathering, exposure to atmosphere over a long period. For ships in service, hand cleaning may be used for very small corroded areas. High-pressure water blasting is superseding grit blasting for ship repair. It is capable of restoring a steel surface to SA 2.5, provided any corrosion has not been allowed to develop. Disposal of the waste material, in this case mainly water, is a main reason for the adoption of water blasting. Blast cleaning using shot or grit is preferred for best results and economy in shipbuilding. It is essential prior to application of high-performance paint systems used today. Pickling, which also gives good results, can be expensive and less applicable to production schemes. Flame cleaning is much less effective, and hand cleaning gives the worst results. Water blasting is mainly a ship repair process. After the steel is blast cleaned, it may be several months before it is built into the ship and finally painted. It is desirable to protect the material against rusting in this period, as the final paint will offer the best protection when applied over perfectly clean steel. The formulation of a prefabrication primer for immediate application after blasting must meet a number of requirements. It should dry rapidly to permit handling of the plates within a few minutes and working the plates within a day or so. It should be non-toxic, and it should not produce harmful porosity in welds nor give off obnoxious fumes during welding or cutting. For some high-speed welding processes, it is necessary to remove the primer in way of the welds to avoid porosity. After cutting and welding, areas of damaged primer are usually strip-coated by hand to cover the affected steel and retain the primer protection against corrosion. The primer must also be compatible with any subsequent paint finishes to be applied. Satisfactory formulations are available, for example a primer consisting of zinc dust in an epoxy resin. Some shipyards where work is entirely undercover and where the steel is used quickly may dispense with primer. Given the sophistication and cost of modern, long-life coatings, their application is critical to performance. It is common for shipyards to take complete units and blocks, once all the hot work is completed, for final coating in a controlled environment. So-called paint cells are temperature and humidity-controlled buildings. The units are driven into the cells using self-elevating transporters. The units are then blasted, if no primer has been used or the primer is degraded and unsuitable for overcoating. Once cleaned, the coatings can be applied in near-ideal conditions. Hull and internal coatings are applied. Where the units are to be joined in the building dock, unpainted areas are left. These are completed after the hull welding, using localized protection from unsuitable weather conditions. The paint system applied to any part of a ship will be dictated by the environment to which that part of the structure is exposed. Traditionally, the painting of the external ship structure was divided into 3 regions. 1. Below the waterline, where the plates are continually immersed in sea water. 2. The waterline or boot topping region, where immersion is intermittent and a lot of abrasion occurs. 3. The top sides and superstructure exposed to an atmosphere laden with salt spray, and subject to damage through cargo handling. However, now that tougher paints are used for the ship's bottom, the distinction between regions need not be so well defined, one scheme covering the bottom and waterline regions. Internally, by far the greatest problem is the provision of coatings for various liquid cargo and saltwater ballast tanks. The ship's bottom has priming coats of corrosion-inhibiting paint applied that are followed by an anti-fouling paint. Paints used for steels immersed in sea water are required to resist alkaline conditions. The reason for this is that an iron alloy immersed in a sodium chloride solution having the necessary supply of dissolved oxygen gives rise to corrosion cells with caustic soda produced at the cathodes. Further, the paint should have a good electrical resistance so that the flow of corrosion currents between the steel and seawater is limited. These requirements make the standard non-marine structural steel primer red lead in linseed oil unsuitable for ship use below the waterline. Suitable corrosion-inhibiting paints for ships' bottoms are pitch or bitumen types, chlorinated rubber, coal tar epoxy resin, or vinyl resin paints. The anti-fouling paints may be applied after the corrosion-inhibiting coatings and should not come into direct contact with the steel hull, since the toxic compounds present may cause corrosion. Generally, modern practice requires a complete paint system for the hull above the waterline. This may be based on vinyl and alkyd resins or on polyurethane resin paints. Red lead or zinc chromate-based primers are commonly used. White finishing paints are then used extensively for superstructures. These are usually oleoresinous or alkyd paints that may be based on non-yellowing oils, linseed oil-based paints that yellow on exposure being avoided on modern ships. Where aluminum alloy superstructures are fitted, under no circumstance should lead-based paints be applied. Zinc chromate paints are generally supplied for application to aluminum. Severe corrosion may occur in a ship's cargo tanks as the combined result of carrying liquid cargoes and sea water ballast, with warm or cold sea water cleaning between voyages. This is particularly true of oil tankers. Tankers carrying white oil cargoes suffer more general corrosion than those carrying crude oils, which deposit a film on the tank surface, providing some protection against corrosion. The latter type may, however, experience severe local pitting corrosion due to the non-uniformity of the deposited film and subsequent corrosion of any bare plate when sea water ballast is carried. Epoxy resin paints are used extensively within these tanks, and vinyl resins and zinc-rich coatings may also be used. The immersed hull and fittings of a ship at sea, particularly in coastal waters, are subject to algae, barnacle, mussel, and other shellfish growth that can impair its hydrodynamic performance and adversely affect the service of the immersed fittings. Fittings such as cooling water intake systems are often protected by impressed current anti-fouling systems, and immersed hulls today are finished with very effective self-polishing anti-fouling paints. The functional principle of these systems is the establishment of an artificially triggered voltage difference between copper anodes and the integrated steel plate cathodes. This causes a minor electrical current to flow from the copper anodes, so that they are dissolved to a certain degree. A control unit makes sure that the anodes add the required minimum amount of copper particles to the seawater, thus ensuring the formation of copper oxide that creates ambient conditions precluding local fouling. A control unit can be connected to the management system of the vessel. Using information from the management system, the impressed current anti-fouling system can determine the amount of copper that needs to be dissolved to give optimum performance with minimum wastage of the anodes. Anti-fouling paints consist of a vehicle with pigments that give body and color together with materials toxic to marine vegetable and animal growth. Copper is the best-known toxin used in traditional anti-fouling paints. To prolong the useful life of the paint, the toxic compounds must dissolve slowly in sea water. Once the release rate falls below a level necessary to prevent settlement of marine organisms, the anti-fouling composition is no longer effective. On merchant ships, the effective period for traditional compositions was about 12 months. Demands in particular from large tanker owners wishing to reduce very high docking costs led to specially developed anti-fouling compositions with an effective life up to 24 months in the early 1970s. Subsequent developments of constant emission organic toxin anti-foulings, having a leaching rate independent of exposure time, saw the paint technologists by chance discover coatings that also tended to become smoother in service. These so-called self-polishing anti-foulings, with a lifetime that is proportional to applied thickness and therefore theoretically unlimited, smooth rather than roughen with time and result in reduced friction drag. Though more expensive than their traditional counterparts, given the claim that each 10-micron increase in hull roughness can result in a 1% increase in fuel consumption, their self-polishing characteristic as well as their longer effective life, up to 5 years protection between dry dockings, made them attractive to the shipowner. The benefits of the first widely used self-polishing copolymer, SPC, anti-fouling paints could be traced to the properties of their prime ingredients, the tributyl compounds or TBTs. TBTs were extremely active against a wide range of fouling organisms, and they were able to be chemically bonded to the acrylic backbone of the paint system. When immersed in sea water, a specific chemical reaction took place that cleaved the TBT from the paint backbone, resulting in both controlled release of the TBT and controlled disappearance or polishing of the paint film. Unfortunately, it was found that the small concentrations of TBTs released, particularly in enclosed coastal waters, had a harmful effect on certain marine organisms. This led to the banning of TBT anti-fouling paints for pleasure boats and smaller commercial ships in many developed countries, and the introduction of regulations limiting the release rate of TBT for anti-fouling paints on larger ships. The International Convention on the Control of Harmful Antifouling on Ships, 2001, subsequently required that 1. Ships shall not apply or reapply organotin compounds that act as biocides in antifouling systems on or after January 1, 2003, and 2. No ship shall have organotin compounds that act as biocides in antifouling systems, except floating platforms, FSUs, and FPSOs built before 2003 and not docked since before 2003. The final phase out of TBT paints was in 2008. In theory, ships could retain the paint if it was sealed under another coating, but in practice TBTs are no longer at sea. Note that organotin means an organic compound with one or more tin atoms in its molecules used as a pesticide, hitherto considered to decompose safely, now found to be toxic in the food chain. A biocide is a chemical capable of killing living organisms. Anti-fouling paints subsequently applied have generally focused on either the use of copper-based self-polishing anti-fouling products, which operate in a similar manner to the banned TBT products, or the use of the so-called low-surface energy coatings. The latter coatings do not polish or contain booster biocides. Instead, they offer a very smooth, low-surface energy surface to which it is difficult for fouling to adhere. When the vessel is at rest, some fouling may occur, but once it is underway and reaches a critical speed, the fouling is released. Thanks for watching. Please keep subscribe and share.